All right, today's lesson should be pretty chill. Now, we talked a lot about velocity yesterday. What's velocity?
Speed with a direction.
Love it. It's speed with a direction. We have all agreed to stick to a set of norms here. This direction, your velocity be what? Use a better word. Positive. What about that direction? How about that direction? How about that direction? Could you just throw a whole wrench and say, nope, I like the opposite, and then use the opposite?
Yes.
Terrible idea, but you could. We won't, and I won't. I can't stop you from doing it. Okay. Now, beyond that, all of a sudden, we get a couple weird ideas, or at least one weird idea. We're going to start today following up our discussion of velocity stuff. Remember, we looked at speed versus time. We looked at the slopes of those and saw that, hey, our displacement, our distance, all these things can vary. Today, we'll just briefly touch on this idea that I think we've referenced, relative motion. Now, we're always moving. All of us, all the time. The Earth is spinning around its axis, and the Earth is rotating around its axis and around the sun, and the sun moves around the solar system, and the solar system's moving. Everything's moving all the time. We don't feel it, though. When we are driving down the road and we look at a car passing us, we don't see a car going 70 miles per hour if it's passing us on the highway. We see a car going like 5 miles per hour. Why? We're going pretty much the same speed, right? And what it really comes down to is this relative motion. So, turns out where we view something from, we've used this word before, I pick a specific what point to set up a problem? Reference point. We all have a single reference point. Typically where you start, you're going to use as the origin, but it really does vary depending on the context. So what winds up happening when we think about relative motion is that if we see a change in reference point, if we see a change in our reference point, we get a change in our interpretation. Now, there's only one situation where this isn't the case, and it's a weird idea. I can spell, I promise. Interpretation. Okay. One weird example. Now, for this, we're going to take a look and we're going to just draw some really simple pictures. And your pictures can be simpler than mine, but I'm going to go as simple as I can and still show a context. Imagine you're on like a train car. I'm not going to draw a fancy train. A train car. Okay, cool. You're a platform on a set of train tracks. Don't even care about the car around it. Okay, so check it out. We're going to consider a few different comments with this in mind. If you're on a train car, and here it is, it's beautiful, and it's just a flat surface with two wheels. Maybe it's a big skateboard. I don't really care what it is as we're looking at it. But here's what I want us to think of. We are standing on this thing, and we're going to make it a train car so it'll be like the right size. Okay, this person's standing here. Are they moving or not on this first example? No. Okay, so if I want to say they're not moving, we would say their velocity is what? 0, and what should the units be? Meters per second. Now, I will be using vectors or specific lines, and you'll see them here in a minute. I'm just going to say, hey, it's a point. There's no size to it. There's no magnitude. Doesn't even make sense to talk about direction. Okay, this person is standing here, just kind of doing their thing, and all of a sudden, they see a ball, or they throw a ball, and let's say here's the ball that they throw, and it has a velocity of 10 meters per second. Now, I haven't been clear yet. Not entirely. How fast is the ball moving?
0 miles.
So, we're moving at 0 meters per second. The ball moves at 10 meters per second. I've given you a speed at this point in time. If I want a velocity, what else do you need? We got the speed, 10 meters per second.
Acceleration, distance.
We're getting there.
Direction, time.
Direction. We need to have a direction. So, this is going to impact the way this looks. If this person throws a ball that direction, in the positive direction is how we're looking, what's it going to look like the ball is doing to them?
Not moving. Or if moving.
They throw a ball, they're not moving, and I throw a ball at 10 meters per second. When I view that motion, what does it look like to me?
It's going
Away from us, how fast?
10 meters.
Okay, so we are away from us at 10 meters per second. And that shouldn't be a surprise because that's what we see all the time. In front of us, we could view as positive. Doesn't matter what direction we're facing. You want this gear switch on your desk? I can throw it. Okay. Now, all of a sudden, this specific situation, if you need to write it, because if you might forget it, who threw this ball? Whoever this is, right? They're the ones that threw it. Now, all of a sudden, let's throw a little weird mix in here. Here's like example A, we'll call it. There, the person threw it. It looks like it's traveling away from us at 10 meters per second. Okay, example B, and I'll switch colors every time. Beautiful car with this person standing on it. And they're throwing this ball. We're getting crazy with their art. Weird proportions, but that's okay. Let's say this time, this person is moving. And let's say at 5 meters per second. Now, I'm not going to do this perfectly and I'm not going to measure it, but I want you to notice something that I've done just intentionally and that I want you to start thinking about. We already have a vector or a directed line segment, a direction and a size. This is a vector. It looks like a ray, or you guys might not have seen rays yet. It looks like it starts here and goes that direction, but only goes this far. That's, in my mind, what I call 10 meters per second. In this example, they're moving slower, right? What happens with the size of it? It's roughly half. The size or a magnitude of our vector is important, especially when you're starting to do stuff. So let's say this person, same thing, I'm going to have them throw a ball, and I'm going to put some dashes here to indicate that they've thrown it. And let's say they throw it the exact same speed. The velocity of that ball is still 10 meters per second. And to indicate the direction, I will just throw it here, and we'll say, look at that, it's still 10 meters per second. From the thrower's point of view, how fast have they thrown that ball?
5.
So there's options. The person is either throwing it at 5 meters per second, or 15, or 10. From their perspective, from thrower, what does it look like to them?
5 meters per second.
Why 5?
Because he's traveling at 5 and he's throwing the ball at 10.
So check this out. I don't want to hit anybody with stuff, but I'm going to find something that I can throw. I don't really have much to throw in here.
Oh wait, you're still hitting. You're still throwing Max.
All right, so check it out.
I got something to throw.
Oh, I got lots of stuff to throw too. Cool. Check it out. Right now, I'm just guessing speed. I'm going to throw this, okay? I can see it traveling away from me that fast. Probably not 10 meters per second, but that's okay. I'm walking. I'm going to throw it the same. Does it look any different from my point of view?
No.
You think so?
No.
If I'm running and if I throw a ball here, or if I'm walking forward and throw a ball the same energy, I don't see a difference in it. It still looks from my perspective that it's going 10 meters per second. Nothing has changed in our perspective because whether we're moving still or not, we're throwing it forward from that platform. Which little part of this that we have to overlook, we're throwing it from the platform, right? Which means when we throw it, how fast is it already going? So how fast are we moving? We're already moving this fast and we throw it away from ourselves there. All of a sudden you may start to pick up that, man, there's going to be some weird perspective stuff happening. We're going to add another person. From the thrower, it's still 10 meters per second. That's how fast the person measured this. 10 meters per second. Okay, we're going to throw this person into this. And I'm not really going to make stuff 3-dimension. We have this other person watching. And they're just standing here. No velocity. They're not moving. How fast does the ball appear to move to them?
Probably slower. No? I think 10.
Talk it out with your neighbors. Try to justify it. From the person standing still watching, what does it look like? It's natural for this to get weird. From stationary observer. So I'll just say from stationary. Or I'm just going to call this person P2. Person 2. P2 isn't moving in either of these situations. They see the 5 miles per hour that the person's moving at initially. They tack on the 10. It's going to look like it's traveling at 15 meters per second. Now, this idea can feel strange, and it should feel strange, but when we make it a context it's more common, easy to think about. A car passes you on the highway. Does it look like it's going 70? No, because you're probably going like 65 and it's passing at 70, and to you it looks like it's traveling how fast? Sorry. 5 miles per hour faster. What if there's somebody standing on the side of the road watching? It looks like they're traveling at 70, right? So they're both right, they're just working from different reference points. Is there anything that we could do to make this situation even a little bit stranger?
Yes.
What?
I don't know.
I like the confidence with which you spoke at, though. So we're going to draw another one.
Maybe a guy moving slower, but like still on a platform.
So we could change the speed. I am going to let him still be on the platform, but we're going to switch it up this time. We have a person riding on this platform, and we're just going to keep their 5 meters per second. That's a nice value just to keep with. P1 here. They're moving this direction at 5 meters per second. So nothing has changed from their perspective. Okay, person 2. We're going to let them stand here, right in front of them. Maybe there's 3 dimensions. I'm not worrying about it. This time, person 2 is throwing the ball. Let's say at 10 meters per second in that direction. Now, what sign should I put on this if we're going that opposite direction? Good. Negative. Okay, so all we're dealing with is what do they see? Person 2 sees the ball leaving their hand going how fast? They'll see it as 10, right? We're just working on that negative. Person 1 is going to see the ball coming at them. How fast?
15.
They're going to see it coming toward them at 15 meters per second because they're going toward the ball as well. Those speeds, those velocities combined. Now, if you're looking at that going, no, it'd be -5 because you're trying to cancel stuff out. You are working from a different reference point. That's all that's happening. My main point with all of this, person 2, we see -10 or just 10 meters per second for our speed. Person 1 is going to see that ball coming at them how fast?
15.
15. Now, these references obviously make a huge difference in how you view the situation. There's one place in the universe where this does not work. One example, and it's really weird to think about. If I'm traveling down the road at 100 feet per second and I throw a ball at 100 feet per second, somebody standing still is going to look like he's traveling at 200 feet per second. Like, they'll just add up. We ignore air resistance for now. When we think about this weird, let's instead get on a spaceship, and we're going 99.999% the speed of light. Like, almost as fast as the universe's speed limit. You cannot go faster than the speed of light. And they turn on their headlights. They turn on their headlights. We'll pretend they have headlights on their spaceship, which doesn't make sense, but maybe they do. What happens if we're going the speed of light, which is the speed limit of the universe, and we turn on light to shoot out in front of us, what happens? So maybe the speed of light changes. That's a good thought. I'll tell you, it can't. It doesn't. From their perspective, they see their light leaving them at that speed, at the speed of light. It's going twice as fast as them, from their perspective. From somebody outside, it will not seem that way. Space distorts and changes shape depending on how fast you go, and there's a whole lot of crazy stuff related to it. Laws don't get broken. That's a big idea from probably like the only famous physicist that you guys know of.
Einstein.
Albert Einstein. His theory of... So he's also pretty famous. Do you know Einstein's famous theory of general... Relativity. Now, he's talking about the same thing. He's just thinking on more kind of interesting scales. Okay. The big takeaway. Does your perspective matter?
Yes.
Yeah, and all these people are right from their perspective. And that's an important thing to make sure that we connect with. Okay. One more little piece of this section, and then we're going to hopefully have some time to just work through a few ideas. One more idea. If I was going to, let's say I'm going to shoot something at you guys. Just going to throw something at you. I can throw a steel ball, or I can throw a styrofoam ball of the same weight and mass. Which one would you rather be hit with?
The foam ball.
Why?
Oh, no, actually, no.
It's the same
No.
thing, no?
Are they the same?
They're the same thing. You said same mass and... What? Wait, repeat
So,
it.
same size. Sorry, I might have said same mass. I haven't even
You
spoke.
said mass, yeah.
If I have this thing that weighs, I don't like that texture. Not one bit. Not even a little bit do I like that. I can throw a styrofoam ball at you or a steel ball of the same size. So same circumference, same everything. Which one would you rather be hit with?
Foam ball.
Why?
Less than heavy.
The density.
Less volume. No.
So the density is certainly different. The volumes are identical.
Yeah.
The mass is different. What's mass?
Something what's inside.
The amount of stuff inside. Oh, whoa.
Pause.
Time. Yeah, I'm cool with that.
Yeah.
Cool. All right. So we get one more idea. Momentum. And we're going to make this vocab. Momentum. Now, when I think of momentum, my mind does not go to physics. I think of sports. What's momentum in sports? Could be running. If you're watching a game and you say, oh man, this team has momentum, what does that mean? They're what? Keeping it together. What do you mean by that?
Like their points are ramping up.
So possibly, sometimes there's a lead change in a game, whether it's baseball, soccer, doesn't matter to me. Like scores change, right? If a team is down 3-0 and they're just getting whooped, and they score a goal, and then 5 minutes later they score another goal, and then 5 minutes later they score another goal, who is now the favorite? The team that's getting scored on 3 times in a row like that, or the team that's scoring the goals? They have momentum, and that's a common phrase that we use, just especially with sports. Gentlemen, make sure you're paying attention back there, Klein. Okay. So when we're looking at this, turns out that same idea, if a team has momentum, they're hard to stop. And that's a huge benefit if you're in competitive sports. Same idea works exactly in physics. We get a Greek letter that's not going to look like a Greek letter to you, which I hope is a good thing. The Greek letter, if you guys draw a lowercase p, how do you draw it? My guess is you probably draw a vertical bar and then this.
Yes.
Everybody draw it like that?
I do like this circle.
Yeah.
Interesting. You do that?
No, like I don't pick up a pencil though. I just go like.
Okay, so your lowercase p is going to look very similar to this. We use the Greek letter rho to represent momentum, and it starts at the bottom and you come up and it looks like that. It just doesn't quite connect. In reality, what letter am I totally cool with you using? P is fine with me for this situation. Okay, when we look at momentum, whether it's in sports or physics, it's the same idea. Momentum is simply defined by the product, which tells us we're doing what operation? Multiplying. So the product of an object's velocity and I'll use and instead of that so it doesn't look like a plus, mass. Okay. Now, for whatever, I doubt we have overlap on this, but maybe, if you guys watch shorts on YouTube, have you ever seen the program where they shoot like different sized objects at different speed at the earth and it shows what the damage would be? Has that ever shown up on yours?
Like a gun, like shooting like a
It's like a video game, but yeah.
No.
I don't know how much overlap we have. I don't know what it is to search up. But let's check this out. If I wanted to make this wordy definition, it's all fine and dandy, but it's what I care less about. We're going to do a simplified formula using words just to make sure we all get it. And we're going to do the actual symbol formula to make sure we all have that as well. If you don't need the words, is that okay?
Yeah.
I'm okay with it as long as you know what we're talking about. So, how, just using words and like times and equals and stuff, what would this equation look like? Momentum equals what? How would you write the product of velocity and mass? What letter do we use for mass? So we'll just say right now it's just mass times what? So V for what? Velocity. Boom. Here's the wordy version. Okay. It's easy to calculate. Momentum is equal to mass times velocity, just like distance is equal to speed times time. And we're going to be able to do the same triangle trick with this if we need to. Instead, I would much prefer, rather than writing these words because that's not very convenient, let's use our symbols. What do I use for momentum? P, I'm going to call it rho, but sure. Equals, what's mass? M times V. Now, a couple things that I want you to be aware of, but I'm not going to be hardcore with it. Does velocity have a direction?
Yes.
And a size? Which means it's a what?
You're right. Vector.
It's a vector. You do not have to include it, but that's a vector, and this is a vector. Momentum also has a size and a direction. Okay, the last little part of this that is always super important, and it's going to get more and more important as we go. How do you measure mass? What unit is typically used for SI?
Meter or kilograms.
Kilograms. We would have kilograms here times what's velocity? Meters per second, which means for our purpose, and this is always weird, the unit is derived, Liam, you said that word a second ago, the unit for momentum. is, and this is just ugly, and it's going to keep happening, which is why the unit game becomes so important. Kilogram meters per second. Okay. This is not a unit that makes sense naturally as you're thinking about it. It's strange when we start dealing with them. It's why the unit game and the fraction stuff gets so important. Yes, sir.
Is that just saying like how fast the object is moving compared with its weight?
So, sort of. We're getting really close to the idea of kinetic energy. We're not quite there, but we're getting close. So momentum plays a role in kinetic energy. Now, for these, we're going to do a couple quick examples, and we are going to get to use everything that we've done so far. Just to help, in case you hate doing the little bit of algebra to rearrange an equation, if you need it. We know that what is equal to something times something? Rho is equal to times v. And I just want to highlight here, notice, it's exactly what we did with speed and time. If you need to solve for mass of an object and you know its momentum and its velocity, what do you do with them?
Wait, mass
Divide by-
rho over v.
Rho by v, right? What if you want to solve for velocity?
P over m. Or rho
So
over
yeah,
m.
p or rho divided by the mass. I'm cool with that. Momentum over mass. Now, we can move that equation around just like we did the other. We now have like two big ones: distance, speed and time, momentum, velocity, and mass. Okay. With that in mind, let's do one, maybe two examples, and let's check it out. Did we use Usain Bolt in an example yet?
Maybe.
Who is he?
Fastest.
Okay, so we're just going to do a quick example. I'm going to give us like a shortened version of this. Let's say that we have Usain Bolt, and I'm just going to say Bolt. Bolt, when he ran his world record time, had mass of 94 kilograms and ran the 100-meter dash in, anybody know the time?
9.6.
So you're super close, 9.58. Okay, world record time, 100 meters from stop to finish, 9.58 seconds. It's insane how fast he is. He even slowed down at the end if you never saw the video. Okay, let's say that we have the following. He crosses, and we're going to make this easy for us because we don't have acceleration. If he crossed finish line at his average velocity. Find momentum. Find his momentum. Okay. Pictures when solving problems in here are not required at this point. I don't know that they'll truly be required all year long, but sometimes they can help. Why do you think I made the point to talk about his average velocity rather than just saying he crossed the finish line? What happens to somebody's speed as they start from the blocks and then they start sprinting? If you were to take their speed like 100th of a second in, are they moving very fast? How about half a second in? Are they going faster? How long do you think it takes for them to get up to full speed?
Just good 2 seconds.
Say it again.
Good, like 2 to 3 seconds.
Like probably about that, especially if you're an Olympic sprinter. But there's a whole amount of time where he's speeding up, right? And then in reality, he coasted across the finish line when he did this, which makes it even crazier. But we have a few things to find. So we're going to go through this process and making sure that we get what we're after. How do we always, or what do I require us to write down in these problems?
Find.
Given,
Given,
and
Good. All right, so we're going to let random numbers help us out here. I want to know some of the given information and what you'd like me to write down. Number 15. Oh, it might be Ronaldo. How about number 7?
it gives you 94, the mouse is 94 kilograms.
Okay, how would you like me to write that down?
And equals 94 kilograms.
M is 94 kilograms. Love it. Okay, so I know M is 94. Number 14. So what is 100 meters? So it's not written explicitly there, but I'm going to rephrase this. He's running the 100-meter dash, right? From start to finish, what distance does he cover?
100 meters.
Good. Now, decision. We can either write D for distance, or I would prefer this. Delta X was our change in position because we use X for this. Do you want me to write D or delta X? Okay, I'm fine with that. 100 meters. So we know those two things for sure. How about number 11, something else? And I'll write that down. What is that? What is it equal to, though? What's 9.58 seconds? That's a measure of time, T. Okay. Anything else you know, Klein? I don't think so, realistically. I'm going to call on you guys just, every time I see people talking, it's going to keep happening over and over and over and over. 4 corners, that's a comment. Okay. What do I need to find to make sense of this problem?
Average velocity.
Okay, so I'm going to teach you guys a shorthand just because it will show up. Average velocity. There's a few ways we can do this. I like subscripts. AVG is fine for that. Yes, miss? Yeah, that's fine. You're going to miss this problem, just so you know. Okay. Okay, it'd be better to wait to the end, but if you're going to pop, yeah, you can go. Okay, we need the average velocity. Don't know it yet. We'll get it. Now, I'm going to switch color because I have the ability to do so. What else might we need? Do we need anything else? Oh, maybe not. We have the average. Cool. Awesome. Now, here's a fun part, and just because I'm out of space, I'm going to put it right here, but in your notes, you may not have that problem. I want the equation and the work that goes into this. Oh, we do need something else. What are we asked to find? We're looking for his momentum. So we also need this. Okay. We need the velocity to get the momentum, right? So we should probably knock that out. How do you find average velocity? Okay, so check this out. We're just going to say check. We have this is equal to distance over time. And notice if we're not dealing with anything crazy, I'm okay if we just use V because we understand we're talking about the average. If you want to keep using those subscripts that say AVG, I'm fine with it. How far did he go? What's the distance here? 100 meters over how much time? 9.58. All right. Seconds. With a calculator, either the one that's in your desk or the one that you have, give me an approximation. His average velocity. I would go to hundredths of a second.
Okay, so 10.44.
10.44 is our first. Can I get a second with that? We're just doing that division. Okay, 10.44. Second that, somebody. Okay, I have a second. If you get anything other than 10.44, please let me know. Awesome, we're done. He was going 10.44 meters per second, right? Am I done?
No,
Why?
you have to find momentum.
Oh my, momentum. Okay, so when we plug this in, let's check it out. I've given us everything that we need, hopefully in a nice way. I'm going to put a little star there because I'm going to use it again. It's not my final answer, but that value is important. When we use this, I know that momentum, rho, is equal to what times what? Mass times velocity. Do we know the mass of Usain Bolt? 94 what? Kilograms. Now, I think it's ugly to do the actual math and the units game inside of it. So what I typically do is I will stick the units down here, right underneath. Kilograms times, what's his velocity? 10.44. And then this is going to look strange, but underneath, I hate this fraction outside of just writing it down as an answer. This is meters per what?
Second.
Why do I write it like that?
So S becomes on the bottom.
So I can see exactly what works out. When you take 10.44 times 94, shout it out when you have it.
981.36.
981.36. Waiting for confirmation. 981.36? Okay. Now, we're looking for momentum. And if I do the math with my units here, I get kilogram meters per second. Is that what it should wind up in? Is that how that's how we measure it, right? Nothing crazy happens here. Okay. For this, same thing. I'm not going to make you write it in your notes, but it wouldn't be a bad idea. Give me context with this. Yes, sir. Yeah, hustle. There's a sign-out sheet there. Don't take your phone. Okay. What is 981.36 kilogram meters per second? Whose momentum? Bolt's momentum at the finish line is approximately 981.36 kilogram meters per second. Okay. That unit is wonky. If we compare this with something, just to show you, if I toss a baseball at you really gently and it hits you, it might hurt a little bit, right? Momentum of that guy, roughly 0.15 meters per second. Okay, if you have a person walking, and we have large surface area, so it's less crazy, but imagine somebody of human weight that was just a little tiny point, and they're walking into you this fast. Is it going to hurt? Yeah. Absolutely it's going to hurt. A regular person walking at just walking speed is like 100 kilogram meters per second. A car traveling down the interstate, 70 miles per hour, if you get hit by it, is it going to hurt?
Yes.
About 45,000 kilogram meters per second. This is not insanely large, but it's a lot for one person, especially depending on how much size there is behind it. Is this super hard? Okay,
Yeah.
I want you guys to do one more with your group, your neighbors. I'll be coming around. I want to check it to make sure that we're cool. I'm going to rearrange it a little bit. Yo.
Alright, so you're telling me the 987.36 kilogram meters per second is that, like, let's say you're standing, right? And if he hits you, that's how much weight he's going to put out?
That's how much momentum you're going to be struck with.
Okay.
We'll make the relation to energy
Alright,
later
that's
on.
it, yeah.
It's a lot. It's absolutely a lot. Okay, one more with your group. I'm going to caveman talk and write. So check it out. We have part B or example B. I want the momentum. Find momentum of a 2 kilogram ball striking the ground at 30 meters per second. All right, looking at this thing, what do I know? One thing, let's see, Vincent E. One thing I know about this problem. So, I'll just stop right there. What's 2 kilograms? What do I represent that with? Mass, perfect. Okay, let's see. Raylene, give me something else I know. I know the velocity, even though that word wasn't thrown up here. Meters per second is velocity. What is the velocity? Good. What do we have to find? The momentum. You could write the word momentum if you really want to. I like the letter rho, or a P if you'd rather. Don't know what it is yet. Now, looking at this, how do you calculate out momentum? What times what?
Meters and velocity.
So not meters, careful.
Oh, mass.
Mass times velocity. Do we know the mass?
2 kilograms.
Hey, we do. I'm going to write my kilograms down here. Do we know the velocity? I'm going to write my meters per second down here. Those of you who got 60, this problem mathematically is not crazy. I will tell you, though, if you answer 60 on the quiz, test, whatever it is, I'm not giving you points for it. Why? Oh, my label. When we start getting stuff that looks like the same everywhere, these labels are going to be the difference between understanding and showing that you understand and not. Just throwing it out there. If we wanted to set up a problem where I give you the momentum and the velocity of it, could you find me the mass? You would just cover up in that triangle, whichever one, and solve it as follows, right? Okay. Yay, nay. Feels super hard, feels okay, somewhere in between. Okay. We'll check for tonight.
I don't understand. Can
You will get to do it for us, and for everybody will get to do it for yourselves here in a second. Don't call people out. We get homework. Okay, so we're in physical science. Wrong thing. Okay, if you want to grab a sheet of paper, this is going to be homework 2.2 is what we're about to start. Don't do it in your notes. You will be handing this in tomorrow, just so you're aware. Okay, today is the 10th, and I'll zoom way in here. Okay, we did lesson 2.2.2, and what was our main focus today? Momentum, and I'll post a video here shortly. Your homework tonight. Remember, just so we have it, name. Next line down is what?
Date.
Not date. I don't really care about the date.
Period.
5th hour, and I'll even cool with just shorten it. 5th FISI.
What page?
So we'll get there. Last thing you're going to put is homework 2.2. You will find this waiting on page 48. It's actually 48 and 49, but I'm just going to write 48. And I want you guys to do 14 through 21. Okay, top left of your page, this is what I want. Name, 5th FISI, and then the homework number and the assignment. Because when we get later in the year and you just hand me something that has no page, no nothing, I'm not going to take the 10 or 15 minutes to figure out which assignment you just handed me. Cool. All right, we got like 5 minutes to start right now. You will likely be able to get 1 or 2 problems done first.